तो ये आपको स्क्रीन नजर आ रही है?
Yes, sir.
Okay. So let's continue with our practice problems. Although we are beginning this new chapter uh, in this book, but you know the spring elements are not new to you, so we have covered this in previous lectures. You only need to distinguish between two types of springs: the translational spring and the torsional spring. And torsional spring means that you have a twisting load basically, and translational spring means that you have a translational load. Now, to distinguish between the two symbols, this looks more like a resistor, and this looks more like an inductor. Okay, although actually springs um, they will look very much the same. So one more thing you need to remember is uh, so when you are using this particular symbol, it's clear that it is a translational spring and it's a torsional spring. But sometimes remember these are models. Okay, so you have a spring model, so you have a translational spring model and you have a torsional spring model. Now, if you have a problem in which you are given something like a rod or some other structure like a beam, अब यहाँ पे तो नहीं पता ना कि आपने आपने इसको ये वाला मॉडल लगाना है, ये वाला मॉडल लगाना है. And what do we mean by that model? Actually, we are only modeling the deformability or flexibility. Okay, so rigid, in the first part of this course we said that okay, things are deformable or rigid. Okay, so if they are not rigid, then you model that property as a spring. And how do you know whether you model something as a translational spring or as a torsional spring? कैसे पता चलेगा? तो उसका ताल्लुक सिर्फ सिंबल से नहीं है, सिंबल तो आप बाद में ड्रॉ करेंगे ना, उसका ताल्लुक लोड से है कि the load, when the load is translational or normal load, tensile, आपको नाम याद होंगे ना, टेंसाइल और कंप्रेसिव, दोनों का हम नॉर्मल लोड कहते हैं. तो हम ट्रांसलेशनल स्प्रिंग की बात करते हैं. एंड व्हेन वी हैव अ टॉर्क एज ए ट्विस्टिंग, तो उसको हम फिर रोटेशनल कहेंगे ना. यहाँ पे एक चीज बनती है जो कि कंफ्यूज करेगी आपको, वो ये है कि लेट्स से मेरे पास एक रॉड है और उस रॉड को मैं अगर ट्विस्ट ऐसे करता हूँ अबाउट इट्स ओन एक्सिस, फिर तो टॉर्जनल है, क्लियर है. Let's say I need to, there is a rod and let's say it is fixed here and I am pulling it like this. So अब this is not twisting, ये twisting नहीं है, ये orbit motion है, ठीक है ना. और orbit motion में you will still model this as a translational spring. उसकी reason ये है कि maybe we go to the next page to explain that. But before that, I want you to pay attention to this thing which we call free length. Yeah, free length. जो L आपको यहाँ नजर आ रहा है, फ्री लेंथ है. फ्री लेंथ वो लेंथ है जिसमें आपने इसको विदाउट लोड कोई नहीं है या बैलेंस है, ठीक है. सो जो इक्विलिब्रियम, जो इसकी इक्विलिब्रियम पोजीशन है, अनस्ट्रेच्ड हम इसको कहते हैं, अनस्ट्रेच्ड और अनकम्प्रेस्ड और अनश्रंक भी कहते हैं इसको, अनश्रंक. सो उसको हम कहते हैं फ्री लेंथ. एंड डिफ्लेक्शन इज द डिफॉर्मेशन. बेसिकली डिफॉर्मेशन के से पहले जो लेंथ है उसको हम फ्री लेंथ कहते हैं. Now one thing is important is that when you specifically explicitly show free length separately, then it's very easy to understand the meaning of x, deflection. But sometimes you don't want to show this. You don't want to show this detail. You just want to focus on the deflection. And so in that case, you just like this symbol, you will have a symbol which will represent the reference, and then you say x. So this symbol means that x is to be measured from the free length, okay, from the equilibrium. And now we can see at this table. So in this course, you are not expected to derive expressions like this. They are more from mechanical and civil engineers, but you are expected to be able to read these tables. So if you are provided a table, um, हेलो वालेकुम सलाम। अच्छा मेरी क्लास अभी शुरू हो गई है तो हाँ तो ये 3 बजे ख़त्म हो जाएगी। ठीक ठीक थैंक यू। ओके so you are expected to be able to read these tables. So for example, if I look at the first entry, this is what we call a coil spring, and although it's a coil spring, but we will still use this symbol which looks like a resistor. Okay, हम वो उस तरह से coil नहीं करेंगे क्योंकि वो वाला that will give us a torsional spring, तो ये वो बात नहीं है, ठीक है। Now to understand the expression, you see some geometry. So this is the central line and the diameter is 2r, which means r is the radius. So वो r यहाँ पे r है denominator में, r cube के form में, n is the number of coils, yeah, just like you have in an inductor, and wire diameter, जो wire है which has been coiled, that also has a diameter of its own. तो वो d भी इधर आ रहा है, and this is the expression for translational spring constant. अब इसमें जो चीज डिफरेंट है, जो जियोमेट्री में नहीं है, वो आपका है g. So although you are familiar with E, which is the modulus of elasticity, Young's modulus, this G is the modulus of rigidity. Yeah. So elasticity is when you are focusing on the normal load, and modulus of rigidity is important when you are twisting something. No, sorry, not twisting. When you are considering the shear, yeah, shear stress. आपको याद है हम when we had this stress strain curve. So if this is a normal stress, तो फिर ये कर्व है, यहाँ पे आपको E मिलेगा, and if you have shear stress का जो कर्व बनता है उसको हम फिर कहते हैं modulus of rigidity. So so one thing is now clear, that in all these different figures, the expression depends on 3 things basically. The expression depends on 3 things. It depends on geometry, the length, dimension, number of teeth, and so on. It also depends on how you loading. For example, यहाँ पे ये लोड ऐसे आया हुआ है, and the kind of support, loading as well as support. तो लोडिंग ये नॉर्मल लोडिंग है और ये सपोर्ट दोनों साइड पे वर्टिकल सपोर्ट है, ठीक है। यहाँ पे ये सपोर्ट है आपका, यहाँ पे कोई सपोर्ट नहीं है, नो सपोर्ट. सो द टाइप ऑफ सपोर्ट और द एब्सेंस ऑफ सपोर्ट एज वेल एज लोडिंग. अब देखो यहाँ पे लोडिंग कौन सी हो रही है, नॉर्मल लोडिंग हो रही है, एक्सियल. इसको एक्सियल लोडिंग भी कहते हैं, एक्सियल लोडिंग. दिस इज ऑल्सो एक्सियल लोडिंग. So all the dimensions like L, W, H, yeah, all these are part of geometry. And to see why it's important, for example, all these 3 objects have the same shape. You see, they have the same length, the same width. If you look at it from the side, the same height, but in spite of that, these formulas are different. Why? Because they all have different, if you look at this, they all have the same load. Okay. The only difference here is that it's at the side and it's in the middle, but you see the support is different. Here the support is simply supported. Here the support is from the side, but from one side, the other side is free. And here both ends are fixed. So this end is fixed, and this is different from that, क्योंकि ये vertical support है और ये side wise horizontal support है. Yeah, the support is from the sides. So now we have understood that the importance of support and loading as well as geometry, but we also need to know the material properties कि ये चीज बनी किस चीज से है, रॉड स्टील है, ये लकड़ी है, ठीक है ना, is it rubber or metal or steel or aluminum. So उसके लिए इसीलिए आपको नजर आ रहा है कि ये जो कांस्टेंट्स होता है ना, E, G, E, 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 these are they reflect the importance of materials. हर मटेरियल से जब आप वो बनाओगे स्प्रिंग, तो स्प्रिंग कांस्टेंट उसके हिसाब से बनेगा. सो स्प्रिंग कांस्टेंट डिपेंड्स ऑन थ्री थिंग्स: मटेरियल प्रॉपर्टीज, support and loading, and geometry. Okay. Now we don't have an extensive table of torsional spring constants, but I think there are two shapes which you will see most often: a simple coil spring with a diameter d, and of course the wire thickness, wire diameter small d, number of coils, and elastic constant, yeah, modulus of elasticity. So the spring constant, the torsional spring constant, to distinguish it from the translational spring constant, if you write K here, you have to write KT here. This T will remind you that we are talking about a torsional spring constant. So, and the next shape, the second shape, which will occur frequently, is the hollow shaft. So you have the external diameter, you have the internal diameter, and this is hollow. Okay. So d to fourth, small d to fourth, pi times g divided by 32L. So for example, if you have a solid shaft, then you have just, you don't have any hole in it, so that d will be 0 here. So if I set d to 0 in this formula, then I have kt torsional torque for a solid cylindrical shaft will be pi times g times d to fourth divided by 32L. Okay, so you can use this for both cases, for hollow as well as for the um, solid one. So you are only expected to be able to use these tables. Okay, one more thing which we need to understand here is that it is easier to see here why we are calling it a spring. And when you know that, you know the loading is vertical, and you know that, okay, the x, this deflection, remember we use x for deflection. So here this deflection is horizontal because the loading is horizontal. Here the loading is vertical, remember vertical loading, so we can imagine that the deflection will also be vertical. Here it's also straightforward, horizontal loading, so we can imagine that the deflection will also be horizontal. अब यहाँ पे ये इसलिए आसान है ये दोनों कि इसमें जो लोडिंग है और जो स्प्रिंग वाली प्रॉपर्टीज है, जो जिस तरह आप ये स्प्रिंग बनाएंगे वो सेम डायरेक्शन में है. ये वर्टिकल है तो ये भी वर्टिकल है. हियर इट्स अ बिट कंफ्यूजिंग क्योंकि ये जो इसका जो लेंथ है वो हॉरिजॉन्टल, मेजर जो पोर्शन है वो हॉरिजॉन्टल ही है, ये वाला साइड बहुत कम है, और जो लोडिंग है वो वर्टिकल है, विच मीन्स कि यहाँ पे जब आप डिफ्लेक्शन शो करेंगे, वो डिफ्लेक्शन ऐसे शो नहीं करेंगे, वो ऐसे शो करेंगे वर्टिकली, which means that if I want to model this if I want to model the deformation, deformability of this beam, the spring, I don't have to write the spring like that, because this will suggest horizontal loading. This will be wrong. So I have to model this as a vertical spring. Why? क्योंकि लोडिंग भी वर्टिकल है और डिफ्लेक्शन भी वर्टिकल है. ये बात समझ आ गई? डोंट लुक फॉर दिस डायमेंशन. ये लेंथ अगर हॉरिजॉन्टली है या बीम ऐसे राइट साइड पे आपको नजर आ रहा है, लेफ्ट साइड पे, तो इसका मतलब ये नहीं है कि इसका स्प्रिंग भी ये बनेगा, स्प्रिंग इसका ये बनेगा, ठीक है, क्योंकि स्प्रिंगीनेस रिलेट्स टू द लोडिंग एफ एंड द डिफ्लेक्शन, ये दो जिस डायरेक्शन में होंगी स्प्रिंग हमारा उस डायरेक्शन में होगा। And now we can get to some more stuff. Before I get to the specific examples, there are times where you have to work out the equivalent stiffness of more than one springs. So here, for example, we have two springs, K1 and K2. They both are supported by the same surface, and the one end of each of them is connected to something which applies a force F. So this is your loading. Now, one thing is very clear, because this end and this end both are connected here, so they both will have a common X. X will be common, okay? Which means that if and you see here, this is why I showed you on the first slide that when you don't want to explicitly show this free length, then you show this X by using a similar symbol, yeah, and it will represent the reflection from the equilibrium. Reflection by definition is from the equilibrium. तो यहाँ पे आपको ये चीज नजर आ रही है, इसका फ्री लेंथ हमें नजर नहीं आ रहा है इस डायग्राम में, and that's why the meaning of this X is that this X is deflection from its free length, and we don't even need to know that free length, okay? But one thing is clear, that both the springs will have the same X. Now, if I ask you, how about this F? Will F be the same for both springs? For example, I want to write Hooke's law. So assuming that it is a linear spring, linear spring का मतलब ट्रांसलेशनल नहीं है, ठीक है? डू नॉट कंफ्यूज ट्रांसलेशनल विद लिनियर. लिनियर का मतलब ये है कि नॉन लिनियर नहीं है, वो जिसका स्ट्रेस स्ट्रेन कर्व है वो ऐसे नहीं है, इस रीजन में है, ठीक है? So if I now want to write the equations, the equations of Hooke's law for this spring, so मैं क्या लिखूंगा? K1 times X, this X, will give me the force for the first spring, ठीक है? अब आप मुझे ये बताएं कि ये फोर्स ये दोनों पे सेम अप्लाई होगा या ये डिवाइड होगा? आपके ख्याल में क्या होगा? If you can't understand this you imagine yourself as if you are applying this force, and imagine there are 100 springs all in parallel. So just imagine how much force you will have to apply if you want the same displacement in all of them. You will have to apply more and more force. So it means that the force is basically divided among the springs. तो इसका अपना फोर्स होगा, इसका अपना फोर्स होगा. So let's call that F1 and F2, okay? So this is something you need to remember, that two springs are said to be in parallel if they have the same displacement and the force is divided among them. If I now add the two equations, I'll get K1 plus K2x, and the sum of these two forces will give me F, the combined force. So which means that if I want to represent this combination of two springs by a single spring with an equivalent stiffness Ke, yeah, then that Ke is K1 plus K2. Why? Because I know that Ke by definition is F over X, and f over x from this equation is k1 plus k2. Okay. So it's very unfortunate but true that because this looks like a resistance, two springs in parallel, though it does remind you two resistance in parallel, but the formula for two springs in parallel is very different from two resistors in parallel. वो parallel वाला formula इस पे नहीं लगाना, यहाँ पे उल्टा series वाला formula इस पे लगता है, ठीक है? So when the springs are in series, you have to remember that it should not behave like two resistors in parallel. It behaves like two resistors in series. So now if you have two springs in series, K1 and K2, and then you apply a force to one of them. Now here, because this end is only connected to x1, so x is the displacement only of k1. No, actually x will be the displacement of both k1 and k2. Okay, x is the displacement of this whole body. So k1 और k2 की अपनी अपनी displacements होगी, because उनका end common नहीं, यहाँ तो end common था ना, तो common end का मतलब ये है कि x भी common था. Because the ends are different, so k1 will have its own displacement x1, k2 will have its own displacement k2 x2, and they both will give you the same force. Why? Why will the force be the same? उसको समझने के लिए आप ये कह रहे हैं कि लेट्स से ये जो पॉइंट है बीच में, लेट्स से यू हैव अ फ्री बॉडी डायग्राम for this. Okay. Or maybe you can think of these two springs. So एक spring इधर है, एक spring इधर है, ठीक है ना? Because they are interacting at this point, so यहाँ पे जो action reaction pair होगा वो same होगा. Action reaction pair. So the force applied by this spring on this spring will be the same as the force applied by this spring on that spring. Because these forces are equal, they will both equal the same force. Okay. So that's why the same force is transmitted through both the springs. Now, if I want to, I don't want to add these two equations in this form. I would rather write this as x1 equals f over k1 and x2 equals f over k2. The reason I wrote it in this form is that now I can add these two equations. So if I add x1 and x2, I'll get x, because I know x is the combined displacement. And this will give me f over k1 plus f over k2. Yeah. So if I want to write this as an equivalent spring, that will give me f over ke. Yeah. Because I know that f must equal kex. So x must equal f over ke. And if I now cancel f on both sides, I know that 1 over ke, the equivalent, is 1 over k1 plus 1 over k2. तो अब ये आपको पैटर्न वही मिला कि when the springs are in series, their formula looks like the resistors in parallel. And when the springs are in parallel, their formula looks like the resistors in series. And I don't think this is difficult to remember, okay? Even if you forget the formula, you can still work it out. So, but what you need to remember, formula से ज़्यादा आपको ये पता होना चाहिए कि पैरेलल हम उनको तब कहते हैं जब x सेम हो, ये बहुत ज़रूरी है. सीरीज हम उनको कब कहते हैं जब उनका फोर्स कॉमन हो, because the same force is transmitted. Now this is this will provide you some practice now, that you have three springs in series, and they are both, the combination of the three is then in series with another combination of two. So these two are in parallel, these three are in series, and then the resultant of this and the resultant of this are in series again. So अब इन दो का जो equivalent होगा वो क्या होगा, इन दो का बताएं, because they are in parallel, तो हम क्या लगाएंगे यहाँ पे, we'll simply add them, so which means that it will be k plus k, which is 2k. यहाँ पे क्या है इन तीनों में, because these three are in series, so हम यहाँ पे वो फार्मूला लगाएंगे कि 1 over k e is 1 over k plus 1 over k plus k, और इसका आउटकम ये होगा कि this will be 1/3 of k. Remember, 1 over k plus 1 over k plus 1 over k is 1 over the equivalent question mark, and that means that the question mark is k over 3, k over 3. Okay, now these two are in series. Series का हमें पता है कि if I now want to represent this by a single ke, single equivalent stiffness, so I know that 1 over ke is 1 over k third, a third of k, plus 1 over twice k. Okay, and that means that ke is the product of the two, k3 1/3 times twice k plus 1/3 plus twice k. So इसमें k, yes, yeah, so इसमें k cancel हो जाएगा, so you will be left with, and you multiply by 3 the numerator and the denominator, it will be 2k and 1 plus 6, so it's 2k over 7. Okay, 2k over 7, yes. Okay, this question will provide you another opportunity to check your understanding whether you can spot parallel versus series. So let's say you have a table with 4 identical legs and that supports a vertical force. So you have a vertical force and it is supported by a table with 4 legs. So एक बात तो क्लियर है कि ये चारों जो है ना ये they are supporting the same force, the force will divide, and because it's the same table, the table top is rigid, you assume the table top to be rigid, so ये ground पे भी इनका common base है और table top भी commonly touch कर रहा है, so they will have a common displacement and the force will be divided, so they are in parallel. So you have four legs in parallel, and each one of them, the solid cylindrical legs are made of the metal with a given modulus of elasticity, which means that if you take any one of them, you will see a rod, okay, with modulus E, and each one of them has a length 1 meter, so L is 1 meter, and diameter is 0.0. Remember, for a solid rod, we use capital D for the diameter, and we use small d for if you have a hole in it. Because there is no hole, so d is small d is 0. And now we can now compute the equivalent spring constant due to the legs. So all we need to know is the spring constant of each spring, k. Yeah, and n, because they are all in parallel, so it will be k plus k plus k plus k, which is 4k. So I know that the equivalent will be 4k, but the question is, what is k? The k के लिए I need to look inside and in that table for a solid cylindrical shape. This is torsional, so we are not looking in this. Here, for our purpose, we will look at this shape, solid rod. Okay. So EA over L. This is the formula. So K for each leg is EA over L. L in our case is 1 meter. E is this value, yeah, twice 10 to 11 Newton per square meter. And A is pi by 4 D squared, and D is 0.03 meters squared. Yeah. So maybe you could have simplified this here, E pi by 4 D squared, and then L. L comes from here. And then you plug these values, so you will have the value of K, and you multiply that value of K by 4, and you will have the equivalent spring constant. So the trick was to identify that they are in parallel. कोई क्वेश्चन है इसमें, इस एग्जांपल में? Let's move on to the next example. And here you have another example of two springs. So if you model this as a spring, now अब हमें यहाँ पे कैसे पता चलेगा कि ये लोडिंग एक्सियल है या टॉर्क है या वर्टिकल है? हाउ डू वी नो? तो डायग्राम में तो कुछ नहीं दिया हुआ हमें. सो बट देन वी नीड टू, जब हमें डायग्राम में कुछ ना हो तो हम फिर क्या करते हैं? वी लुक एट द स्टेटमेंट, and the statement is to determine the expression for the equivalent torsional spring. तो इसका मतलब ये है कि यहाँ पे लोडिंग जो है ना वो torsional लोडिंग की ही बात हो रही है, twisting. For the stepped shaft shown on the right. Stepped का मतलब ये है कि दो है इसमें. So now we have to model this as a torsional spring, and we have to model this as a torsional spring, and they are in series. Okay. So let's call this K1T, T for torsional, K2T, T for torsional, and we can now write the expression K1T, K2T. And once we do that, because they are in series, their equivalent KT will be 1 over KT will be equal to 1 over K1T plus 1 over K2T, and this will be able to solve this by just multiplying the two, K1T times K2T, K1T plus K2T. That we can do. So, but the question now is that how do we work out these expressions? So for them, we need to go to the table of torsional spring constants. So instead of a hollow shaft, we look for solid shaft, set D to 0, which means that our formula will be pi g d to 4th 32L. 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 और यहाँ पे ये D1 है इसका D2 है, इसका L1 है, इसका L2 है, इसका D2 है. ठीक है. G इज कॉमन. G अगर ना भी है, you don't need to know G, क्योंकि यहाँ पे आपको सिर्फ एक्सप्रेशन कैलकुलेट करना है. You don't need to write the actual values. So you plug these two values here, and you have an expression for the equivalent torsional spring constant. ये आसान वाले केसेस थे, ठीक है ना. अब यहाँ पे थोड़ा सा टेढ़ा केस है जिसमें it may not be so easy to figure out whether the springs are in series or in parallel. So what you see here is that the figure shows a horizontal force. This is the horizontal force which is applied only to the first spring, and the force is acting on a lever. This is your lever, yeah, that is attached to two springs. Now because this force is attached to both the springs, so this force can affect both the springs. Now how, it is not clear. Assume that the resulting motion is small enough to be only horizontal. इसका मतलब ये है कि यहाँ पे चूंकि मोमेंट्स यहाँ इन्वॉल्व हैं about point O, so you can have this motion, but the assumption is that the motion is so small that you can approximate this motion to be horizontal only. ये सिर्फ ऐसे ही मूव करेगा, ठीक है ना, ये वाला मोशन नहीं होगा. Determine the expression for the equivalent spring constant that relates the applied force and the resulting displacement x. अब यहाँ पे बहुत जरूरी है कि equivalent spring constant के E को इसने define ऐसे किया है F over x. अब F ये है और x ये है. इसका मतलब है कि हमारी चॉइस है कि हम x कौन सा लेते हैं. मैं अगर चाहता तो मैं इस क्वेश्चन को चेंज कर लूं और मैं फिर कोई और यहाँ पे डिफ्लेक्शन ले लूं, ठीक है. So it is actually how you define KE for a particular, क्योंकि ये एक स्प्रिंग नहीं है ना. एक स्प्रिंग में तो ये आसान होता है. फॉर एग्जाम्पल अभी तक हमने जितने भी एग्जांपल किए हैं वहां पे हमें पता था कि एक ही स्प्रिंग है. Even if you have two springs, you have a common X here. Here you have two springs, but there is a combined X here. So यहाँ पे वो गिवन है कि what he means by the equivalent spring constant is the one that relates the applied force to the resulting displacement x. अब क्वेश्चन ये है कि are these two springs in parallel or in series? क्या ख्याल है आप लोगों का, स्प्रिंग पैरेलल में है? क्योंकि if we know they are in parallel, then we don't need to do anything. We just write this expression, KE will be equal to K plus K. So the answer will be 2K. So do you think that is true? ये पैरेलल में अगर है तो क्यों है, नहीं है तो क्यों है, ये बताएं. पैरेलल के लिए क्या कंडीशन है? यहाँ पे कौन सा कंडीशन मैंने रिपीट किया था इधर? They must have the same x. और सेम एक्स इसलिए कि ये सपोर्ट भी सेम है दोनों का और ये एंड भी, दे आर बोथ ड्रिवन बाय a common point, although the force divides, but the overall force is actually acting on both ends. यहां पे ऐसा नहीं है. यहां पे जो आपका फोर्स है F, that only applies to this point. वो और बात है कि उसकी वजह से ये दोनों मूव करेंगे, लेकिन ये सिंपल नहीं है इतना. So what we can see now is that if this end moves by distance x, because this is rigid में you can have this triangle. Okay, if this represents if this line is represented by this line and this is the displacement of this point, this pivot doesn't move, so the center point moves here, and you can now use some trigonometry that if this total length is L and this is half and this is half, this angle is common, so if this is x, what should be this distance? And that means that we can simply use the tangent. So x over L is the tangent of theta. If this is theta, let's say this is theta. So that question mark, the middle deflection, divided by L by 2 should also be tangent theta. So which means that this question mark must be half of x. So अगर ये x है, so this must be half of x. So now what do you say now? They do appear to be in parallel, but they are not in parallel because the two springs have different deflections. Yeah. Even though the force divides, the deflections are different. So when the deflections are different, they are not in parallel. और सीरीज में तो वैसे नहीं है. So ना सीरीज में है ना पैरेलल में है, ठीक है. you still want to relate f and x to one another, तो उसके लिए हम फिर ये करेंगे कि we can have a free body diagram here, और फ्री बॉडी डायग्राम में हम ये देखते हैं कि हम कोई आसान सा कन्वीनियंट सा पॉइंट चूज कर लेते हैं. नाउ the reason we need to choose this point is because we don't want to bother ourselves with these reaction forces. Of course this is a support, तो support पे reaction forces तो होंगे x y दोनों डायमेंशन में. we don't want to concern ourselves with that. हमें सिर्फ f पता करना है. तो f के लिए if I now use the convention, let's say that anti-clockwise torque will be positive. About O, I can now write the moment equation. So kx, अच्छा कोई मुझे बता सकता है कि kx मैंने लिखा है this is a restoring force, ठीक है, restoring force coming from the spring, तो इसमें माइनस साइन मैंने क्यों नहीं लिखा? आपके ख्याल में नॉर्मली तो हम माइनस साइन लिखते हैं ना, या क्यों नहीं लिखा मैंने? I can ask the same question here. This is F, and when I the spring force will be upward. Now when you say upward, you represent that by the arrow, because this arrow is opposite to this x, so minus sign आपको अलग से लिखने की जरूरत नहीं है, ठीक है ना? You need the minus sign when the arrows are the same, because the arrows are different now. You don't need a minus sign. तो यहाँ पे हम minus sign basically we represented by this opposite arrow. This arrow is opposite to x, तो वो minus sign ऑटोमेटिकली इधर आ रहा है हमारे पास. सिमिलरली इसका जो मिड पॉइंट पे जो टॉर्क है उसकी जो चूंकि डिफ्लेक्शन x/2 है, तो k will multiply x/2 because they both have the same spring constant. So I can now write kx is this force, और इसका जो टॉर्क है about O, it will be kx times this length, which is L. Then the other force kx/2, kx/2 का जो मोमेंट आर्म है वो L/2 है, and the torque for F, और because we take this as the positive torque, तो ये दोनों तो पॉजिटिव है, लेकिन जो फोर्स F है applied force, उसका torque counter clockwise है, that will be negative. So F times L, and we can now cancel L on both sides, and F will be equal to K plus k/4 times x. Yeah? So this is the ratio between f and x. That is what we mean by the equivalent spring constant. The equivalent spring constant would be 5/4 of k. समझ आ गई बात? सो आपने डायग्राम देख के डायरेक्टली डिसाइड नहीं करना कि पैरेलल है या सीरीज है. यू हैव टू एस्टैब्लिश that they will be in parallel only when they have the same deflection. They will be in series only when they have the same force. Okay. And I can change this question by changing this x to x/2, and then your answer will be you have to divide f by x/2. That will be your answer. Okay. So ke in that case will be f/x/2, और ये आंसर चेंज हो जाएगा फिर. Now here is another question which is very interesting, because so far we are talking about linear springs. Okay. And you know, in the chapter on materials in one of the books, we saw that if you plot stress strain, if you have the stress strain diagram, only this part is linear, and then you have this plastic region and nonlinear. So you know about nonlinearity. It's not something new for you. But here we have a different scenario. We have three springs and they are all linear by assumption. So you assume that each spring exerts a force that is proportional to its compression. So this is just another way of saying that all the three springs are linear. Yeah, it's just a fancy way of saying that. Now you need to obtain the deflection यहाँ पे x है, of the system model shown on the right as a function of w. ठीक है? So you need to express x as some function of w. This is the task. Now how do we do that? Now, because of this gap d, initially the load is only connected to K1. So if this deflection is smaller than d, there are two cases now. Now I have the first case when the deflection is smaller than d. That means that only spring K1 is going to. So if I have a free body diagram for this massless point, let's say I have this massless body and I want to have a free body diagram for this. So one external force is W. The other external force on this body is the spring force, which is K1x. And I'm writing K1x because I know that x is by assumption less than d. जब तक x less than d है, तब तक K2 का कोई force नहीं आएगा इस पे, क्योंकि वो contact ही नहीं है तो force कहाँ से आएगा? So if I now apply Hooke's law here, I will have W equals K1x, which means x equals W over K1. Yeah, if x is less than d. Now if x is greater than d or equal to d, फिर क्या होगा कि this massless object will have one force from the top and three forces from the bottom. The one from K1 will still be K1x, क्योंकि वो तो पहले भी that depends on x. But the force is coming from K2. This is K2 and this is K2. This will not be K2 times x. Why? K2 times x ये मैंने लिखा है लेकिन ये गलत लिखा है. तो वजह ये है कि K2 की जो डिफ्लेक्शन है वो x के इक्वल नहीं है. x में से d सब्ट्रैक्ट करना पड़ेगा. d तक तो K2 अभी शुरू नहीं हुआ. So the value of x which exceeds d, x minus d, is actually the deflection in K2. Yeah? So now if you write the force balance, W will be equal to K1x plus K2x minus d, और चूंकि दो दफा आ रहा है तो it's twice. Yeah? So x in this case will be equal to d plus W over K1 plus twice K2. Yeah? And then you can combine these two expressions, yeah, just like you do in signals in the system. That basically you have two expressions. You have one expression when x is less than d, and you have another expression when x is greater than d. और आप इन दोनों में से किसी एक में इक्वल कर सकते हैं. ठीक है. अब ये प्लॉट मैंने इसलिए किया है ताकि आपको ये पता चल जाए कि although each spring is linear, but the overall system has a non-linear response between load and deflection. क्योंकि ये discontinuity आ रही है, you go from one spring to three springs, और ये this is a non-linearity. So it's possible that you have linear components and the overall system is non-linear. This is one example. Okay. Now in this question, we again will have to figure out whether two springs are in series or in parallel. How do we work that out? So let's read the question. You have an arrangement shown on the right, and there you have a cable that is attached to the end of a cantilever beam. Now cantilever beam, आपको पता है मैंने कहा था कि वो 3 टाइप की बीम्स होते हैं. कैंटिलेवर के लिए जरूरी है कि वो सपोर्ट साइड से हो, वर्टिकल ना हो, या वर्टिकल सपोर्ट ना हो, तो ये नहीं होगा फिर. और दूसरी कंडीशन ये है कि वो हॉरिजॉन्टल सपोर्ट भी सिर्फ एक साइड से हो, 2 साइड से ना हो. सो इफ आई लुक एट दैट टेबल अगेन, यू सी दिस इज नॉट कैंटिलेवर, दिस इज नॉट कैंटिलेवर क्योंकि हॉरिजॉन्टल है, दोनों साइड से है. कैंटिलेवर के लिए आपका सपोर्ट हॉरिजॉन्टल और एक साइड से हो, दूसरा एंड फ्री हो. ठीक है. एंड यू मस्ट रिमेंबर that although the beam is extended horizontally, but because the load is vertical, so the deflection because of the support will also be vertical. So if you want to model this as a spring, वो spring ऐसे नहीं होगा, वो spring ऐसे होगा. ठीक है, it would be a vertical spring in spite of this horizontal look. Now what you do is that is your, so this is your beam now, this is the beam. Now but you have a cable attached to the end of the beam. So ये जो free end है वहां पे आपने एक cable show किया हुआ है, तो ये आपका cable है. So basically you have two bodies, you have a beam and a cable, और cable beam के एक free end से connected है. Now we will model the cable as a rod. We model the cable as a rod. ठीक है. Now you denote the translational spring constant of the beam by Kb. So इसका मतलब ये है कि you are modeling the beam as a spring with a spring constant Kb, B for beam. And you have a translational spring constant of the cable. So you are modeling the cable as a spring with its own translation constant Kc. अच्छा, इस क्वेश्चन में आपने देखा होगा कि जो सिंबल्स आपको बता रहा है explicitly, so you should not be worried about this table. इस टेबल में जो ये फार्मूलाज दिए हैं ना कि ये इसका फार्मूला ये होगा और इसका ये होगा, यू आर नॉट कंसर्न विद दैट. अगर ये होता तो हमें ये फार्मूला इधर से लगाना था. केबल वाज ए रॉड, केबल के लिए हमें लगाना था, क्योंकि बट दैट इज नॉट द पॉइंट. ओके, वहां पे उसने सिंपली इसको के सी कह दिया, इसको के बी कह दिया, एंड मूव ऑन. यू आर नॉट सपोज्ड टू नो द डिटेल्स. जो चीज आपने करनी है वो आप पढ़ लें. So let's say you are given these two expressions, and now the further piece of information given is that the displacement x is caused by the applied force. इसका मतलब ये है कि जो केबल जिसको हमने रॉड के तौर पे किया हुआ है, जो उसकी डिस्प्लेसमेंट है वो F की वजह से है. इसका क्या मतलब है कि जो फोर्स F है, लोड, वो इस स्प्रिंग पे लगा हुआ है, इस पे नहीं लगा हुआ. ठीक है, वो इस सिर्फ एक पे लगा हुआ है. And of course, because this spring is connected to that spring, so we are connecting these two by a point. अब इसका ये एंड फ्री है, इसका ये एंड यहाँ पे फोर्स F लगा हुआ है, और ये जो x है, x is the displacement. या अच्छा, अब यहाँ पे इसने इंटरेस्टिंगली जो डिस्प्लेसमेंट शो की हुई है ना, यहाँ पे जिस तरह हमने यहाँ पे बहुत जरूरी था कि this was when I say that when you have two springs in series, this is an overall displacement. अब ये नहीं कहते कि ये x चूंकि इधर है तो सिर्फ k1 का डिस्प्लेसमेंट है, नहीं. ठीक है ना, ये ओवरऑल डिस्प्लेसमेंट है पूरे सिस्टम का. तो यहाँ पे भी ये है कि you have this x is, क्योंकि इसने ये x केबल या बीम के लिए शो नहीं किया हुआ, वो उसने अलग शो किया हुआ है by using a symbol. आपको मैं बता चुका हूँ कि जब आप इस तरह का सिंबल यूज करते हैं with an x, so this symbol does not only represent the support, it also represents the equilibrium position. So basically x is only the deflection of the overall system away from the equilibrium. So which means for us that this x is the overall displacement. And now are the two springs in series or in parallel? अब यहाँ पे न सिर्फ ये पैरेलल तो बिल्कुल नहीं है, अब ये सीरीज हम क्यों कह सकते हैं कि सीरीज है? क्योंकि जो ये फोर्स है, this force will apply to Kc, and because these two objects, these two springs are interacting at this common point, यहाँ पे जो एक्शन रिएक्शन पेयर है वो सेम होगा, which means that the same force will transmit there. अब याद होगा हमने जब गियर्स को मॉडल किया था, तो गियर्स में भी whenever gears were interacting, there was a common force between the two. Action reaction force allows us to establish that. So yes, they are in series. Now what is the equivalent spring constant for this arrangement? वो तो आपको पता है कि 1 over Ke equals 1 over Kb plus 1 over Kc. Okay, and this को आप solve करें, you will have your equivalent spring constant. Now the next one, this is also complicated, and I don't think this is a case of series or parallel, but we still need to solve the problem. So you have an arrangement of springs on the right. Basically you have two springs with constants K1 and K2. The displacement x, this displacement of this end, is caused by the applied force F. Okay? And remember, there is no spring here, no spring. Springs are only to the right. Okay. And assuming the system is in static equilibrium when x is equal to 0. That's just another way of saying that we are measuring x away from the equilibrium. And the angle theta, अब ये बड़ा important assumption है, the angle theta, ये theta है, is small. अब इसका मतलब पता है क्या है small का हमारे पास normally एक मतलब ये होता है कि we assume that sine theta is equal to theta, but it also means that tangent theta is also equal to theta, because cos theta will be 1 when theta is small. And this will be very important for this problem. Determine the equivalent spring constant Ke for the arrangement where F equals Kex. So F ये है, X ये है, and you want to work out this ratio F over X. अच्छा, अब इसके लिए जो चीज जरूरी है वो ये है कि if you draw the free body diagram of this rod, which is massless because we are not assuming the mass there, so then you have this pivot point O, और इस pivot point पे you have one force upward अब यहाँ पे when you apply this force, this will tend to move anti-clockwise, yeah? When it moves to go anti-clockwise, so if this end goes up, this end will tend to come down. So if this end comes down, this spring will be under expansion, yeah? You are stretching the spring. So when you try to stretch a spring, what does it do? Spring कौन सा force apply करेगा? Away, it will try to resist that stretching. So this force from the spring will be upward, which is K2 times. Let's say जो इसका deflection है spring 2 का, let's say that is X2. X is the overall deflection. X2 is the deflection of K2. अच्छा. Now when this body tends to come down, this spring K1 will be compressed. And when you try to compress a spring, what does it do? It will resist that by an upward force. क्योंकि अब इस end को नीचे push कर रहे हैं, so the opposing force will be upward. That will be K1 X1. ठीक है? Now the point is, what is x1 and x2? Now we will see the advantage of this. So if we have a triangle now, if this is the pivot, now because this is a rotational motion में आपको पता है कि rotation में हमारे पास, if you have a center and if you move a little bit, so you have the radius here, and that radius multiplies the angle. So this distance s will be given by the radius times the angle. Okay. Now because theta is small, so this x1 and x2, they both will be just like these deflections. So which means that x1 will be equal to radius times this angle theta, क्योंकि वो theta हमारे पास ये है, ये theta, and x2 will also be equal to the corresponding radius times the same theta. और वो radius यहाँ पे क्या है, because theta is small, so इस केस में radius L2 है, और K2 की केस में वो radius क्या है, L3 है, because the pivot is here. So you have deflection of x1, the reflection of spring 1 is L2 theta, the reflection of spring 2 is L3 theta. Now the question is, how do we relate this to x? Now if you look at this triangle, तो इस triangle में हम ये कह सकते हैं कि tangent theta is equal to x divided by L1. X divided by L1 is also tangent theta. That tangent theta is sine theta, and that tan theta is theta. So which means that now what we call theta is basically x over L. So this will be L2 over L1x, and this will be L3 over L1x. This is now cool because we have expressed the deflection of K1 and K2 in terms of x. Okay. And now we can write the moment equation about point O. तो अब जाहिर बात है point O पे हम कह सकते हैं कि इस साइड पे एंटी क्लॉकवाइज को आप प्लस कह दें और इसको माइनस कह दें. सो 0 will be equal to K1x1 K2x2. इसका जो मोमेंट होगा that will be K1x1 times L2 plus K2x2 times L3 and minus F times L1, because F is the torque of F will be clockwise. And now we can say that okay, x1, ये एक्सप्रेशन इधर हम ले आएंगे, अब ये एक्सप्रेशन इधर आ जाएगा, and if we solve this equation we will have an expression between f and x. That will be your Ke. Okay, so this looks complicated, but you can appeal to the assumptions. That's why I always say that you should never miss any statement in this problem. If you miss out this statement, for example, if you miss out this statement that the angle theta is small, you will never come up with this assumption. And when you don't come up with this assumption, you will never be able to relate x1 and x2 with theta and hence with x, and then you will be stuck here. Okay, so it's an example of that strategy which we explained in the beginning, the SMART strategy. What was S? S was statement, state the problem, model, come up with a model, analyze the model, reflect, and think. Okay, so that was it for today. You have time for questions.